Okay, good morning. All right, so a reminder that we have exam next Thursday, September 29, 6:30 to 7:30 p.m. Try to be there at least 15, 20 minutes early so you get plenty of time to get seated. We will start the exam as close to 6:30 as we can, so make sure you get there with plenty of time to find your seat and get settled down. Also, make sure you find out where you're supposed to go. These blocks are by TA. Look up your TA's name and note the aisle numbers. Once again, if you're in Jeff Zielinski's class, for example, you will want to go in through aisle 3 or aisle 4. If you're in Anna Rose Wolf's class, aisles 5 or 6 will be most convenient for you. And you should have received a seat assignment from your TA. If not, the past Tuesday, then the next Tuesday when you go to recitation again. If you don't receive by next Tuesday, be sure you contact your TA and find out where you're supposed to sit. Finally, it's also very important that you know your 4-digit section number. And like I said last time, this makes sure that your score goes to the right person, goes to the right place. So, your grade is a better reflection of what you did. Okay, and I'll have a lot more to say about the exam next week. So for now, just a reminder. Okay, today we're going to look at 2 sections again. First, we'll finish up 14.5, what we did last time. A little bit more on the chain rule to look at. So in many applications, sometimes you want to find out the slope on a level curve. So you got some function f of xy equal to k, right? That's a level curve when you set z to be a constant. And when you set z to be a constant, you're going to get a curve that's a function, y as a function of x. So let's imagine our curve looks something like that. So on this curve, z is equal to k. And for example, if we want to find out at this point what the slope is, okay? So that's what we're trying to find out here. In other words, we're looking for the rate of change of y with respect to x. Now this is a function y as a function of x now. So dy dx is what we want to find. And let me show you how to do this by an example here. Our function is f of xy is equal to x squared plus y squared. Let's find dy dx on the level curve f of xy is equal to 3. So 3 is our constant k here. You set that to be a 3, then you have a level curve with no z, just x versus y. And that means we got this equation, x squared plus y squared is equal to 3. And one thing you could do is to just do an implicit differentiation like you did in Calc 1. Take the derivative y as a function of x. You could do that. We're going to look at this from a different point of view. So first of all, let me write that down. Option 1. Implicit differentiation Option 2, we're going to end up what's called the implicit function theorem. And I'll show you how that works. Okay, first I'm going to rewrite that function I just wrote down. X squared plus y squared is equal to 3. And I'm going to define a new function. I'll define a function called capital F. That's a function of x and y. And all capital F is this function with everything brought to one side. Okay? So x squared plus y squared is equal to 3. I'll define a new function, x squared plus y squared minus 3. And we know from this is always going to be equal to 0. And now we're back to what we did last time. We have a function of two variables. We're trying to deal with a derivative of some sort. Let's draw the tree diagram here. The function f at the top depends right away on x and y. But y is also an implicit function of x. So y depends on x also. Now we're going to let x be the true independent variable. And you remember from last time, when we step down this tree, if there is a branch, then we'll deal with derivative. So going down this way here, we're looking at a partial of big F with respect to x. Going down this branch here, this is partial of f with respect to y. And here, there's no branching in the tree. It's just straight down. So this is a regular d, dy, dx. Okay? Keep in mind that this is what we're looking for, dy dx. So, if I take the derivative of capital F, I'll take the partial derivative with respect to x. Then to get to x, there are two ways to get there, right? Partial here. And then the other tree, we do partial f, partial y. And then finally stepping down to x with a dy dx. Okay, so that's what we did last time. Just stepping down the tree, remembering to use partial when we have a split. When there's no partial, it's a regular. Now remember, again, we're defining this capital F to be something but ultimately equal to 0. Because it's at 0 here, the derivative of this is going to be ultimately equal to 0. Yeah? Because F is at 0. And now looking at this equation here, what I can do is solve for dy dx. And we see that dy dx is equal to negative of the partial derivative with respect to x over partial derivative with respect to y. Okay. And this will give us the slope of a level curve once we have defined a function capital F. And this right here, this is called the implicit function theorem. All right? Okay, now let's check this out for this example we've been working on. Here's our function f. Fx is simply 2x. Fy is also 2y. So dy dx is negative fx, 2x, right, over fy. Oops, that's a y here, right? Sorry. Yeah. So it's equal to negative x over y. So like I said, this is one option that you could use to find the derivative dy dx by using this. Another route is simply take the derivative of this implicitly, y as a function of x, like the way you've been doing in Calc 1. Okay, let's try this on something else, a slightly more complicated function. E to the y sine of x is equal to x plus xy. Find dy dx. And we'll duplicate exactly the same steps we just took on the last page. Use the result of the implicit function theorem we derived. First, you define that function big F. And all you do is to make everything go to one side. That's all. E to the y sine of x minus xy. And if you define big F that way, then this will always end up being a 0. And now the implicit function theorem says dy dx is negative of f x over big F partial with respect to y. Then you just find the partials, put them together, and see what you get. All right, so what do we get out of fx? This thing on the top, what do we get? E to the y cosine x minus 1 minus y. Good. We agree? Yes? Okay. What about what about fy? E to the y sine x. What else? Minus x. Good. Okay, so there you go. There's the slope, right? It's the same thing you would have gotten if you had differentiated implicitly. In this one here, the implicit differentiation would be a little bit cumbersome because you got y on both sides. You got to collect things and divide things around. It will be a little bit cumbersome, but not too difficult. Whereas the implicit function theorem, simply as an option, would give you the answer a little bit quicker in this case. And this also offers you a slightly different interpretation of the implicit differentiation that you learned earlier. Really, we were dealing with a curve, a level curve of a surface. It's another way to look at it. Okay, then we're going to start a new section, 14.6. In 14.6, we're going to look at something called a directional derivative. And something that's going to play a very dominant role later on, the gradient vector. A lot of what we'll be doing in the second half of the course will have something to do with gradient. This thing is going to be showing up all over the place. So first, let's take a look at directional derivative. A directional derivative is telling you how fast something is changing once you've declared a direction. For example, let's look at this pressure map over here. Okay. Remember, this is the isobaric map here. On each curve, the pressure, the atmospheric pressure is listed. So everything on this curve right here, the area, the location below it will experience 1008 millibar of atmospheric pressure. Everything below this one will experience 1000 millibar of pressure, and so on. So notice what happens if we're starting from this point S right here. And I think that's Sioux City. Right now, standing here, the pressure I feel is 976, right? If I want to get to a place with a pressure of 984, for example, I can go in any direction I want. For instance, to get to 984 by traveling east, I need to cross the entire state. Let's check your geography here. What state is this? Good, very good. We need to travel. That will not be on the exam, so don't worry. So if I need to get there by traveling east, I need to cross the entire state of Iowa, right? But notice I don't have to travel very far if I travel west. I only need to go about a fifth of the distance right here. So that's telling you that how fast the pressure is changing clearly depends on which direction I'm moving. Depends on direction. Okay, and then you can see moving north, there's a different kind of distance we need to go. But that's the idea behind a directional derivative. Given a direction, how fast is certain things changing? All right? Let's first look at the definition, mathematical definition of that. And directional derivative is written this way. First of all, the direction you're going, the direction you're going must be given as a unit vector. I will call that U here just to remind us it's a unit vector. And that's a very, very important thing to keep in mind. So first, here's the notation. Capital D with a subscript u, and then the function f of x, y. This means a directional derivative of the function f in the direction given by the unit vector u. Let's say the unit vector is a comma b. First, let's look at the limit definition of what this really is doing. And what is going on here, this is a generalization of the partial derivative with respect to f, with respect to x and y. Here, we're actually going to change both of those variables simultaneously. So we're going to add x by amount h times the vector, first component of vector a, and y will add y by the amount h, which we're shrinking, times the second component vector b, minus f of x, y, and as usual, divided by h. Okay, so that's the limit definition of that. And this is a generalization of partial derivative with respect to x and y. For example, if I set a to be 1 and b to be 0, then u turns into the I vector, right? That's the I vector. So the directional derivative of that in this instance right here, looking at the limit definition here, with a being 1, so this is x plus h. No b now, so y fixed minus f of x, y over h. And you remember that this is precisely how we define the partial derivative with respect to x. We hold y constant while varying x and shrinking the changing x. So this is how we defined fx in the very, very first place. And you'll see the same thing. If you make a equal to 0, make b equal to 1, then this reduces to a partial derivative with respect to y. So really what a directional derivative is having some components of each of these and then move them together. On a map here, if you move to the east, then that's a partial with respect to x. If you move north, that's partial with respect to y, right? If you move northeast, then that's some kind of directional derivative given here. So what I want you to remember is that this is simply a generalization of what you have already been doing, and it's some kind of sum of the two. In practice, as you know, we normally never use the limit definition to calculate the derivative of anything. So in practice, the computationally more convenient formula is given this way. So here, this will make sense if you remember what I just said, that the directional derivative is some kind of weighted sum of a partial with respect to x and a partial with respect to y. So what you do is if you take the partial derivative with respect to x, multiply that by a, plus the partial derivative with respect to y, and multiply that by b. And remember, u is given by a, b. Which is a unit vector. Okay? All right, so this is the definition of the how we can find the directional derivative. Let's try this on something. Let's find the directional derivative of f of xy is equal to cosine of 2x plus 3y at the point 1, 2 in the direction to the origin. Okay, so function that's changing as x and y change. We want to know at the specific point on this surface right here, and if I travel in a certain direction, how fast is that thing changing? This is exactly equivalent to say we're standing at Sioux City, wanting to move to Kansas City. In a certain direction, how fast is my pressure changing? Here the pressure is given, for example, is given by that function. So that's the idea behind that. Okay? All right, so this is what we need to do. Let's find the partials first. And that's pretty easy. fx minus 2 sine of 2x plus 3y. You agree with that? Yes? Okay. Fy negative 3 sine 2x plus 3y. Okay? Now we need a direction given by a unit vector. So let's see what we're doing here. We want to know what happens when we move from 1, 2 back to origin, in the direction of origin. So here's where we are. We're starting at this point. And I want to go in this direction. So what is the vector that would take me from 1, 2 to 0, 0? Right, minus 1, minus 2. Is this a unit vector? Very obviously, right? This alone has a length of 1. If you put another one there, there's no way this thing's going to have a length of 1. So this guy is not a unit vector. And for that formula to work, we have to make this a unit vector. So let's call our unit vector u. U is, of course, v over the length of v, right? That's how we make any vector a unit vector. So u turns out to be negative 1 over, this is 1 radical 5. Is that right? And negative 2 over radical 5. Now it's a unit vector. And the first component is what we call A in that formula. The second component is what we call B. Okay, and then the rest of this is trivial. You simply put them together according to that formula we have. So the directional derivative of the function at 1, 2 is equal to partial with respect to x at x is equal to 1. Well, let's just write down the xy first, and then we'll plug in a 1, 2. And then A, it turned out to be negative 1 over radical 5. And then Fy, 3. Oh, there's no x here. And then we need B, and B is negative 2 over radical 5. Okay? All right, so now you're plugging x and y at that point. You're looking at 1, 2, and you get negative 2 sine of 8 over radical 5. Negative, negative, positive. So 2 over radical 5 sine of 8 plus 6 over radical 5 sine of 8 so this is what? 8 over radical 5 sine of 8. Okay, so that's the rate of change. For each unit distance you travel in this direction, we expect f to decrease or increase, depending on the sign of that, by this amount. For each unit distance you travel, f will change by this. So this means that we start from 1, 2, moving towards the origin. Each time we move in a little step, f will be increasing by this much. In the context of pressure, for each mile or whatever you move in that direction, then this number will tell you by how much the pressure is going to change. Any question on this thing, on the example we just did? Nope? Okay, good. So let's revisit that formula in the box. We just saw that directional derivative of a function xy is fx of xy a plus fy of xy times b, where u is a unit vector a comma b. Now notice I could rewrite this formula in a different way. I can rewrite this as a dot product of two vectors. The first vector is simply the partial derivatives. Dotted with a unit vector a, b. Right? Do you see how these two are equivalent? Yep. So I simply went from a scalar form back to the dot product of two vectors, which of course is a scalar. And this is our u, so nothing new here. This guy here, we call this the gradient. This is the gradient vector. And the gradient vector, you write an upside-down triangle. It's a vector. And by definition, it is the partial derivative with respect to x in the first component and the partial derivative with respect to y in the second component. So in a different notation, it could look like this. Okay, so that's our gradient vector. And the way you read this thing here, you say del f. Or you just say the gradient of f. Doesn't matter. Sometimes it's written without that gradient arrow over it. Sometimes it's written as grad f. So there are many, many different ways. In different contexts, you'll see different things. So that you'll see in a lot of books, the omission of that arrow over the triangle, the del. I like to write a del there because it's a reminder for me that this is a vector. Without seeing that, it's very easy to forget that we're dealing with a vector. And I would encourage you to do the same, to just as a reminder that it is a vector. So therefore, the directional derivative is also simply the gradient vector dotted with the unit vector u. Okay, now you got two different formulas that you can work with. They're the same thing, of course. Here, if you have the gradient vector, then you find out the unit vector, you dotted the two. Or you can do what we did earlier, find the components of each one of those and multiply them together. All right? Let's try an easy example here. F of xy is the square root of xy. Let's find the gradient vector of this thing. And it's very easy to remember. You take the rate of change with respect to x, put in the I component. You take the rate of change with respect to y, put in the j component. That's your gradient vector. You can think of this as a generalized slope of some sort. It's a combination of two different rates of change put together into one vector. It's a generalized slope. And it has a lot of physical meanings that we'll look at in future parts of the course. But for now, let's just get used to working with this vector. Okay, so what's the partial with respect to x? 1 over 2 root xy, is that it? Times y. Good. Do we agree? Yep. Partial with respect to y, same thing. 1 over 2 root xy times x this time, right? Can we simplify these even more? Yes, we can. So how do we do that? So this is y over 2 root xy, x over 2 root xy. And here you want to consider y as root y squared, for example. And this is root x squared. And if you write it that way, notice we could cancel root y with that root y here and put another root y up there. So you end up getting 1 over 2 radical y over x. Here, 1 over 2 radical x over y. Yeah. Okay? And I know WebAssign is not very picky with simplification, but it's good to know alternate forms if you need to deal with them. So that's the gradient vector. And what does it mean? We'll look at that in a future part. But for now, if you know how to find the gradient vector, one thing you could do is to use that to find the directional derivative by taking the dot product. Okay, so how do you think things change if we deal with a 3-variable function? How do you think the gradient vector will look like? The same thing with another component added, right? For a 3-variable function, let's say w is f of x, y, z, then the gradient of that function f is exactly what you would expect. Now this vector will have 3 dimensions, and the surface, a 3-variable surface is a 4-dimensional thing, and the gradient vector is a 3-dimensional vector, fx, fy, fz. A 4-variable function, you just keep adding components to it, so the gradient vector gets longer and longer for higher dimensions. We can no longer picture what it looks like, but mathematically we could do all of that stuff. Okay, let's do one more example, and then we'll end it there. Let's try this one. We'll take a function that looks just like the one we dealt with. We'll make it radical x, y, z. And this time, let's use the gradient vector to find the directional derivative. At 3, 2, 6 in the direction of the vector -1, -2, +2. Okay. All right, let's do gradient first. And this one will work just like the last example we did. Fx would be 1 over 2 radical xyz. On the top, yz are constant, so the chain rule will give you yz up here. Fy would be xz over 2 radical xyz. And Fz would be xy upstairs. Downstairs is 2 radical xyz. And these can be simplified just like the last example by looking at y as radical y squared, z as radical z squared on the top, and then simplify exactly the same way we did. And this will end up being 1 over 2 radical yz over x, 1 over 2 radical xz over y, and then 1 over 2 radical xy over z. There's a pattern to how these variables are presented in each component. X for the I component downstairs, yz upstairs, y for the y component downstairs, xz upstairs, and so on. Okay? Now remember the directional derivative for this case here would be the gradient at whatever point we're looking at, dotted with u, the vector u. So first we need to evaluate that at this specific point, 3, 2, 6. We also need to find that unit vector u, because this v is clearly not a unit vector. And we'll do those two things on the next page. First, let's find out the gradient at that point. So you put x is equal to 3, y is equal to 2, z is equal to 6 into the gradient vector, and you should get 1, 3 over 2, and 1/2. Then we need a unit vector telling me the direction, right? Unit vector u is the vector v divided by its magnitude. How long is that vector v? That should be very easy to see. 3, yeah? So each component divided by 3 will give me the unit vector. And then you dot these two together, you will get your directional derivative. Del F326 dotted with u, and we get minus 1/3 minus, that's a 1, plus 1 over 3, so we get negative 1. Okay, so that's saying that if you're on that strange-looking surface there, traveling in this direction, each little step you take, the function value will decrease by 1. It could be the temperature, it could be the pressure, whatever. But that's the idea behind the directional derivative. All right, that's it for today. Have a good weekend. See you Monday.